So hello, welcome to today's webinar, DFM and Why It Matters. Again, my name is Brittany Wagman, and I'll be your moderator for today's webinar. Now, before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you're unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. Everyone's line is currently muted and will remain so for the duration of the webinar. This will be an interactive webinar and with a few poll questions popping up throughout the presentation. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We'll have a representative ready to answer your questions directly during the webinar. This webinar will be recorded and posted on the EMA resource page. Once this is posted, we'll send everyone who was registered for today's webinar an email with a link to the recording in the next couple of days. That being said, I want to thank you all for joining us for today's webinar and introduce you to our presenter, Rocco Cavallo. With 31 years of experience in design for manufacturing and quick-turn fabrication, Rocco is a highly dedicated applications engineer for EMA design automation. Start off the webinar with an overview of DFM and some common issues, followed by a brief demonstration. Assuming we have time at the end, we'll field some questions in a formal Q&A. Thanks for your attention, and now over to you, Rocco.
All right, thank you. So good afternoon, everybody. Thanks for joining us today. I'm just going to go ahead and advance my slides here. So what is design for manufacturing? What we call DFM is the acronym, and why should I care? So DFM is the process of designing your printed board to avoid fabrication and assembly problems. And a good DFM will keep your projects on schedule, prevent any late stage changes in the design, and keep your build costs predictable. The traditional DFM checking flow, as most people know it today, is we capture our design intent, we lay out our printed circuit board, we create our manufacturing data, and then we send that off, and it goes under a review or a validation, usually at the fabrication vendor. If issues are found, they're sent back to the layout designer, and he addresses those concerns, and then it goes back through the loop again for validation until finally the data is accepted. So if there's multiple iterations of this causes delay in the project, and that's what we're trying to address through this DFM. So what is the effect of DFM problems? So it can affect our overall yield of our product in fabrication. It can also cause reliability issues and failures possibly in the field. It can lead to a costly respin depending on the type of defect. It can increase my manufacturing costs if they have to adjust or do certain things that will cause a premium charge to be occurred on the project. It can also have a ripple effect by delaying my project. If this is one board of multiple boards in this project and this one's delayed, it affects everything. And last, it also causes me to miss my time to market schedule. So that's how it affects the overall picture, but how does it affect on the design cycle? So it makes our schedules less predictable. If there are communication delays after I've sent the data off to the manufacturer, if they sit on it for a couple hours or a day before they get back to me with their problems they found, there's another delay in my project. So these are the type of things that we want to avoid. It also interrupts my workflow. What if I have multiple projects I'm working on? Now I have to drop what I'm working on. I have to go back and address these issues again. It can also lead to increased development costs because now I'm adding more time to the project that I wasn't counting on having to do. So that's increasing my cost. And again, it's releasing it's delaying my release to manufacturing of my data to get my job going. So what are some of the common issues? And the first one here is a very common one. It's called what we call an acid trap. And this is what we would call an acute angle. So this acute angle causes the etchant to pool into this corner, and when the board goes through a rinse, it doesn't get all of the etchant out of that acute angle in that corner. So what happens is over time, that etchant can continue to eat away at the trace, and eventually it can cause a failure in the field, due to the continued erosion of those traces. Especially in a fine line design, when we have some really thin traces, it could really be a problem. One of the fixes that we can employ is we have built into our tools a thing called enhanced pad entry. So when we actually do routing, it'll snap to the corner of the pin, or it'll snap, out of the center of the pin. So eliminating the possibility for these acute angles. However, if it's turned off, you could get a situation that you see here. The next one is duplicate drill holes. Now, in this screenshot here, this is a coincident via, and this is a common occurrence too. So this is where I have two vias on top of one another, but I've also seen it, in CAD tools in the past, where people try to produce slotted holes or a mouse, breakaway tab, what they call a mouse bite, and they would have all these coincident, drilled holes together, so that they could snap that off when after it's fabricated. And what happens as far as the manufacturer is concerned, what happens is this results in broken drill bits, during the drill operation, because it's a high-speed drill. And this can cause, project delays because, they may send your data back to be reworked. The fix for this one is, we don't have to do duplicated drill holes for slot operations. These are fully supported in our tools today. The next one, this is another very common one, is insufficient annular ring. So an annular ring is the remaining copper that's left after drilling the pad. So what you see here in red, that's the actual copper pad. The gray center here is actually the drill that's going to go through that pad. And what happens is, and especially, we're using some very small vias in the industry today. So what happens is if there's any kind of walking of the drill at all, when we're using these very small vias, you can actually break through this annular ring, and that's what they would call breakout. And so we're trying to prevent that. So what we can do is we can easily increase that annular ring size by changing, the ratio between the drill and the actual copper pad. Next one is missing solder mask. So missing solder mask openings on pads. These are required so that you can reflow or solder parts on the board. So if there's no opening in the mask, we're not going to be able to bond the part if the pad is covered over with solder mask. Chances are the manufacturer is going to find this, but if they weren't able to find it or they missed something, that could cause a problem. So we have a way to detect that now. And simple fix is we just update the pad stack to include that solder mask definition. Same thing with the paste mask. So paste mask opening allows us to put solder paste onto the land pattern so that we can bond the part. So this paste mask is used to create what they call an assembly stencil. And if you had a very small pad, but it was all over the design, maybe 100 times, because it's so small, it could get overlooked. And what happens is when it comes time to assemble the board, they realize, oh my gosh, there's no opening in the paste mask to apply solder to that solder paste. So, that's going to require you to go back and have a new stencil made, again, incurring another delay in your project. And it's a simple fix. It's just something we add in the pad stack. Next one is to be a common occurrence as well, is a copper to board edge violation where we have a trace that's too close to the edge of the board, especially if these boards are, going to go on a conveyor, for auto assembly. Depending on how close those assembly rails come to the trace, it could damage it. So we want to make sure that we move the copper trace back away from the card edge, sufficiently to prevent these errors. Next one is Soldermask slivers. So a soldermask sliver is when they apply solder mask, if these pads are too close together, what happens is they get a very small web of solder mask in here, and it can actually cause it to flake off. And what happens is if it flakes off and this board now goes through reflow, when the solder goes over these pads, it could short these adjacent pads together. So what we want to do is we want to employ a check to make sure that we have sufficient clearance so that we don't have any kind of solder mask webbing. Another one is copper slivers and islands. So what are their small areas of copper, usually around large pin arrays of connectors and things like that. And what happens is we get a floating island of copper like you see here. And what can happen is when the board isn't going through the etching process, these can float off and then land somewhere else on the board and create a short. So we want to prevent that. If they don't come off during the etching process, they could also lead to noise coupling, through this antenna effect. So the way we would cure that is when you're done creating your shapes on your board, there's a command called delete unconnected copper, and that'll remove any islands that it finds out there, and it works very well. Silkscreen to pad violations. So this is where I might have silkscreen lines or text that are on top of pads. So normally we would try to move those away from the pads. If I were to get silkscreen ink on the pads themselves, it can cause contamination of the pad and create solder issues. So we would want to move those off the pads or clip the lines, back away from the pads by a certain amount. Again, this is another thing the fab shop is probably going to find and they'll fix, but it could save you that 1 a.m. call from your fab shop if they find issues. This one's a major issue here. So here I have a connector that's near the edge of the board, and there's a cutout, and I don't have any sufficient clearance to the cutout from the edge of that pad. And the only problem is now, this one was discovered late in the game, so now I have all these routed traces that go up through here. So it's going to take some rerouting and some major rework to fix this problem, because this part now has to move, and there's a lot of other parts and routing that are affected. So this could cause a major delay. So we would look for this kind of error, up front while we're doing placement. And we can do that now. Same thing with components to outlines. So here I have a card outline here that you see is curved, it's coming around here, and this component is too close to the card outline. So it could result in a part getting damaged during assembly. If it's on a conveyor, conveyed edge, it could actually be ripped off the board. So again, we would set a rule to look for these type of things and then resolve them during the placement, long before we get to fab. So DFM problems are often hard to spot manually. And if you look at the overall board here, I mean, at a first glance, it really doesn't look too bad. But as you'll find out, there's some issues with this board. So within design DFM checking, you can see and fix violations in real time. The here is, instead of waiting to the end of the design and then sending it to the manufacturer and having them find the problems, I can find them in real time before I get to that step. So this will help streamline the design process and release of data to manufacturing. It'll eliminate those multiple validation, iterations back and forth, and it'll improve my overall time to market. So here's that design. So let's start to take a look at it. And if you look, there's really, at a glance, it really looks pretty clean. If I open up the constraint manager, you can see now there's a new domain. If I go into this manufacturing section, you'll see there's design for fab and design for assembly rules in here now. And if I expand those, you can see all these different categories that we can look for these, type of defects now. If I turn on the DRCs for the board, you can see it's, going to light up some areas where there's issues on the board. Now, there's a couple ways we can, attack, resolving these. First way is if I hover over the DRC marker, it tells me I have a minimum outline pin to pad spacing. If I right mouse click and do a show element, it'll give me the constraint value. It's supposed to be 1 millimeter. I have 0.992, so it's a little bit too close to the edge of the board. So, first off, I could, maybe do a move here, and I'll select this group of parts, complete my selection, and let's just bump them. I'll just bump them a little bit to the left. And you can see we've cleared up the violation. So that's one way we could do it, but there's actually a better way. So we have now a thing called a DRC browser. Bring up the DRC browser. You'll see I have 171 issues on the board itself. We have design for assembly errors. We have design for fabrication errors. So these are what it found. We can also chart them. If I bring up a chart, it'll actually, if I hover over them, it'll tell me how many violations I have in each category. And you can see the various, categories here. If I drill down into one, you can see I have, like under this general, here I have a duplicated drill hole, for example. So as I'm navigating through the chart, you can see it's stepping me through, and it's taking me to that location. So if I tag that, let's just go ahead and close the chart for a moment. So here's the actual error. So I have that coincident, drill hit on the via here. And one of the things you can do is you can run the database check, and running database check will eliminate those. A lot of people don't know that that's there. So you can see it removes redundant vias. So that's a good way to, go ahead and screen the design, make sure there's no duplicate vias there. If I go back to the DRC browser, and let's go ahead and split my screen in half so you can get a better feel how this works. So if I go into this first error, now you'll notice when I selected this, the text turned black, which means if I bring up my options here, you'll see that a red DRC now turns black, saying that I reviewed it. An unread one is, this bright blue, like a hyperlink, and then there's also a thing called reviewed. So after I've reviewed it, I can also go ahead and check this. So now I've checked that. It says, okay, yeah, I've reviewed that error. So we're gonna fix it. If you wanted to turn it back to unread, you can also right mouse click and turn it back to unread. So that's how that works. So these three errors are all related to this same trace. If I initiate my slide, command, I'm going to take the trace. And I'm just going to bump it away from the card edge, and that clears up those violations. So let's look at the next one. So here I have some mask slivers. If I select the first one, you can see these are clearly, too close to the pad, even though that they're the same net. Electrically, they're okay. However, this is going to cause, manufacturing problems with those mask slivers. So I'm going to go ahead and, start addressing these. So again, in just using my slide, bumping the traces out of the way here, I have an acute angle. I'm going to fix that by using my slide, maybe clean up this trace a little bit. Here I have that cluster of mask slivers. So you can see pretty quickly I can go through the database, and fix a lot of these errors. This one, I'm going to move him out here, give him a little bit more room. And I have an acute angle, so I'm going to fix that. And just about done. It's got a couple more here to address. So you can see the browser's, quite nice. I can kind of step through and, go through each one of the issues and resolve it as I go. And typically, these type of problems, we would wait to get feedback from the manufacturer. They'd send us screenshots, and then we'd have to go and locate all of these things. And, this just makes it a lot easier. So here I have some other acute angles. If I go to this location, you can see now that this one's a little bit unique in the fact that this trace right here, these go to the ground plane, these vias, so it's really not necessary to have this piece of trace connecting these two vias because they both go to the plane. So what I'm going to do in this case is I'm just going to go ahead and remove that C-line segment, and that eliminates the acute angle. And here's that acid. So I'm going to go ahead and slide him away. And just so you know, if you go into, add a trace here, if you right mouse click, this enhanced pad entry is what you're looking for. So if I go to that active layer, for example, and it happens to be on the bottom, you'll see it'll snap to the corner or to the center. So it won't let me create the acute angle. So that's what enhanced pad entry does for you. And I just have a couple more here. All right. So I have a solder mask issue here. So what this is complaining about is I have a masked line error, and what it is this pad right here, the solder mask opening for that is too close to this trace. So that's what the DRC check is flagging. So I need to increase the clearance of that. So if I grab the trace and move it away from the corner, you can see I can clear that up. And here I have another one, same kind of issue. And what we're trying to prevent here is trying to prevent the opening in the solder mask for exposing, giving us exposed copper on this trace, because that could lead to corrosion down the road and things like that. So here I have some missing solder mask, this first one. Now initially you look at this pad and initially you might think it's a surface mount, but it's actually a through hole pad, and it's got actually a square hole. But there's solder mask missing on this. So let's take a look at the pad stack. And in here, if I look under the mask layer, I have solder mask opening on the top, but I don't have one on the bottom. So let's go ahead and fix that. The next one is I'm missing solder mask on all these pads. So again, let's go ahead and fix these. So it should be like a 1.7 and a 3.4. Here I have an annular ring problem. So if I look at these particular pads around this connector, you can see the drill hole is too large for the amount of copper that's left there. So let's increase the pad size to resolve that. Make this like a 1.75. Copy that. Update all the pads in the pad stack, and now we've resolved that. Now you can see there are some other ones in here that you see they're waved. These are waved by default, and what these are is, I'll just go to one so you can see it. These are mounting holes that are out around the perimeter of the card, and they're non-plated holes, and there's a small pad on the top side of the board, and these are going to get drilled away. So they show up as a DRC for that annular ring problem, obviously. But in this case, I know they're going to get drilled away, and I've done that by design. So what I can do is I can go in here and I can put a comment. So I'll just put a little comment in there, and I'll waive it. And again, as you go through and review these, you know, these will go through and, you know, you can check them and say, yes, I've, you know, validated all of these. So you would go through and, you know, review each one of these. I know which ones they are. You can see I've already, you know, pre-waived them. But that's what those are. So right now, my annular rings are all resolved. These are the remaining ones are waived. I have 6 copper spacing issues. So here's a trace that didn't get connected to this pad. So let's go ahead and fix that. And I go to my active layer. Okay. I must have something, I do have something selected. So let's go out here and deselect it. Add a connection and resolved. I have a copper spacing issue here. So here this trace is too close to this via. And you might think, well, what about my normal space to trace DRC rule? Well, this would get it. But there's actually a more exhaustive check that's done as well. And I'm just going to deselect here. So the trace to, you know, pad checks that are done in the manufacturing rules are a little bit more exhaustive. So just wanted to let you know that too. And I've got one where I have a Silkscreen next to a pad here. So normally we would want to move that. So I'll go ahead and move my my text here and just get it away from that pad, and of course it goes away. So all my design for fab errors have been resolved. If I go to my design for assembly, here I have a component to outline issue. And it's this part right here. So here's my little cutout for my connector, and then here I have this, you know, capacitor right up next to it. So let's go ahead and move him out of the way. And again, this stuff can be caught, you know, during placement, because now, you know, these rules look for a component to the, you know, card edge as part of the manufacturing. And then I have some missing paste mask. So again, some of these are waived, and just to tell you what the waived ones are, that's this edge connector. So normally we would not have any solder paste or solder mask covering these, because, you know, this edge card is going to plug into something. So I'm going to look at the ones that aren't flagged here. And you'll see right away, here I have this small pad, and it says, wait a minute, you don't have any paste mask for that. So let's go ahead and fix that. So I'll go into my mask layer. I'm going to go ahead and add that as some paste mask, and I'll update the design. And now you can see the only thing I'm left with are the ones that I waived that I know about. And again, I can put a comment in there. I can tell it, that I've waived it, and so on. Also, when you drill down into the categories, if you want to look at, annular ring, if you want to know a better definition of that, you can hover over this little icon here, and it gives you a little bit of information on that as well. So if I close this now, and we take a look at our board, so now we have a clean design ready to send to our manufacturer. So the whole idea here in summary is, within design DFM checking, you can see real-time violations and fix them real-time. You can streamline your design process so that we don't have those reoccurring iterations between manufacturing. And the overall goal is to improve our time to market. And that's it for me. I'll turn it back to Brittany.
Okay, thank you, everyone. And at this time, I'd like to open up the floor for the Q&A. Please enter any questions you have into the chat now. If we're unable to address your questions immediately, we'll be in contact with you. And just a reminder to all attendees that this webinar will be recorded and posted on the EMA website within the next couple of days. And for our first question here, we've got our CM wants IPC 2581 or ODB++. Bronco, can we generate that in ORCAD?
The answer to the question is yes. We export both. We support both as well as traditional Gerber. The technology is being driven more and more to the IPC 2581 though. But we do export ODB++ as well.
All right, good to know. Is this real-time DFM checking functionality an extra cost?
Great question. So it's actually part of your core tool. If you have ORCAD Standard or Pro, these core checks are now part of the tool. If you have the latest ISR, you would see, the new domain in the Constraint Manager. It was introduced in ISR 38. We're currently at 40. So if you go out and get the update, you'll have the latest DFM stuff.
Okay, good to know. What is the recommended annular ring to pad ratio?
Through my design experience, we used to do 24 mils drill size. So if the drill size was, say 60, we would make that an 84, which gives you a 12 mil gap between the hole and the edge of the pad. So that would be a 24, over.
All right, looks like we got a few more questions coming in. Do you have a template I can import of DFF or DFA rules?
Yeah, that's a great question. So you can export, once you develop the rules in the Constraint Manager here, they can be exported and imported into a new design. So you could, in theory, go ahead and develop different rule sets for different, classes of boards that you have, and then you could just import those rules accordingly. But yes, they are portable, just like our current constraints and technology file.
Okay. Next one here, is tinting and plugging still done over the vias?
Yes, it's a very common practice, especially in BGAs. We would tint and plug the vias with Soldermask to make sure that nothing's going to short underneath the ball grid array, because they do inspect them with X-ray, and that's a very common design practice.
Do you have import options from other EDA packages like Eagle, Altium, etc.?
It's not related to DFM, but yes, the answer is yes. We do import other CAD tools.
All right, I think we'll do one more question here. When you run through the DFM DRC checks, you change pad stacks within the PCB database. Does your DFM tool summarize the changes in a form where you can use it to update your library or send it to a librarian for updating the library?
So good question. So what I was doing, I was just editing the ones in the design themselves, but there's a couple ways you could deal with that. You could have gone into the library, actual library, and updated the pad information like I did, and then refreshed it to the board. So you could do that, and then it's fixed in the library as well. Or if I forgot to do that, I could export all the pads out of the design database that I fixed, and then just copy those over to my library, with those changes that I made. So there's multiple ways you could handle that.
All right, all very good information, Rocco. Thank you. Looks like we have a couple of questions still coming in, and unfortunately we're out of time for today. However, if anyone has questions that were not addressed during the webinar, we'll still be following up with you on an individual basis. I'll be closing the webinar now, and we'll be sending everyone a recorded version of today's webinar with the slide deck within the next few days. Thank you for taking the time to join us today.
Thanks for joining.